Okay, we'll get back to section 4.3, 4.4, and 4.5. I'm covering all three of those sections kind of together here. And we're talking about logarithms. So I mentioned now a couple of times in the last video, make sure that you know this definition, which is the definition of a logarithm. That's very important. Okay. And so there's some problems here where we want to find values of logarithms. Okay, so let's look at some of those next. In part A, what if I want to find the value of log base 2 of 32? Okay, now I'll be honest, the first time that I ever saw logarithms, I was like, oh, you need to use a calculator for everything, right? Like there's no way. So it turns out that you don't really need a calculator much for logarithms, okay? Sometimes you do, but the thing with the calculators is that, I have a log button and I have an ln button, okay? I don't have like a log base 2 button or a log base 3 button. There's a log button, which is log base 10. I'll talk about that here. But I can't do special bases. Okay, so I kind of like that, because it forces you to know the definition of a logarithm then, and not have to rely on the calculator, So anyway, let's take a look at these problems here. We're going to find values of logarithms. So in part A, let's find the value of log base 2 of 32. I'm going to call that y. Okay, and if we find y, we're done. So let's go ahead and use the definition of a logarithm. So y equals log base a of x means x equals a to the y. All right, so x is 32, a is 2, maybe 2 to the y value equals 32. Okay, now I'm in exponential form. And in the last section, in 4.1 and 4.2, we got some practice solving exponential equations. Okay, and I mentioned that will come up again here in this section. Okay, here's where we see that. So the idea is to try to get the same base on both sides. Well, I can do that. I get base 2 on both sides. I know that 2 to the 5th is 32, right? If I take 2 times 2 times 2 times 2 times 2, I get 32. So 2 to the 5th equals 2 to the y, means that if I get rid of the base 2's, so that the power is equal, y is 5. Okay, so log base 2 of 32, that's 5. Okay, let's try part B next. So I need to know the value of log base 3 of 1/27th. Well, let me call that y, and we'll use the definition. We'll convert this to an exponential form. So the x value is 1/27, 3 is the base, be 3 of the y value equals 1/27. Okay, and I'm trying to get the same base on both sides here. So I can do that. I know that 3 cubed is 27. So 3 to the negative third power, that'd be 1 over 3 cubed, or 1/27. So I got 3 to the negative third power equals 3 to the y. Get rid of the base there. And set the power is equal. Looks like y is -3. Okay. Now something that I mentioned in the last video is make sure that you understand that the x values can't be negative, also can't be 0. That does not mean that the y values can't be negative or can't be 0. The y values can and will sometimes be negative numbers. Okay, that's okay. So, and actually, in this graph, if x is any number between 0 and 1, y is a negative number. Okay, if x is 1, log base 2 of 1, that's 0. Okay, because 1, 0 would be on the graph. All right, so how about part C? I need to know log base the square root of 2 of 4. Let's call that y, and we'll use the definition to change that to an exponential form. So root 2 is the base. So root 2 of the y value equal 4 is the x value. Okay, now I'm in exponential form, and so I want to try to get the same base on both sides. I can do that here. So I know that root 2 squared is 2. If I square 2 again, I get 4. Right? So root 2 to the 4th power, that'd be 4. So I got root 2 to the 4th power equals root 2 to the y power. Get rid of the base, the root 2's, and set the powers equal. Looks like y is 4. Okay, so log base root 2 of 4, that's 4. Okay. Part D, I got log of 0.01. Okay, so there's no base here. Now when there's no base written, it's understood to be base 10. You can write the base 10 if you want or not, it doesn't matter. Okay, just know that you got base 10. So we need to know log of 0.01. Okay, let's call that y. 0.01 is the same as 1 over 100. Okay, so I got y equals log of 1 over 100. And let me switch that over to an exponential form. So 1 over 100, that's the x value, equals a is the base, a is base 10, to the y value. Okay, now I can get the same base on both sides, base 10. I just have to think 10 to what power gives me 1 over 100? Well, 10 squared is 100, right? So 10 to the negative second power would be 1 over 100. So I'm looking at 10 to the negative second power equals 10 to the y power. I got the same base, these 10s here, remove the 10s, and it looks like y is negative 2. Okay, so log of 0.01, that's negative 2. Okay, now you can actually use a calculator there in part D. Okay, you most likely can't for these other ones. Okay, even the super high-tech calculators, you can't do special bases with it. So, but let me just show you real quick here, part D. So I got log of 0.01. Okay, that's negative 2, and yes, that's what we're getting. Okay. So I got a base 10 button, a log base 10 button, and then an ln button. I'll talk about the ln function here shortly. Okay. Let's try this one next. So let's get some practice finding the domain of a function. So what if I have f of x equals log base 3 of x plus 1? That's part A. So I know that the overall input value into a logarithm can't be 0 and can't be a negative. So x plus 1, I'm going to have to set that to be strictly bigger than 0 and solve for x. If I subtract 1 from both sides, it looks like anything that's bigger than negative 1 is going to be okay to use as an input value. Anything that's negative 1 or less, we don't want that because that means that we'll have a 0 or a negative number being plugged into the logarithm. You can't have that. Okay. So the domain is the set of all x such that x is greater than negative 1. Now, notice that the base is 3. The base has nothing to do with anything that we're talking about here with domain, okay? How about part B? We got f of x equals log base 4 of 4 minus x squared. All right, so 4 minus x squared can't be 0 and can't be a negative. So if I set that to be greater than 0, 4 minus x squared is greater than 0. Now, if I were to graph y equals 4 minus x squared using what I know about transformations, I'm going to start with y equals x squared, and that's a negative, right? So I flip the parabola upside down, and then the plus 4 means to shift it up 4 units. Okay, so this would be the graph of y equals 4 minus x squared. Now I need to know where we're positive. Well, if you're above the x-axis, you're positive. If you're on the x-axis, you're equal to 0. And if you're below the x-axis, you're negative. So I guess another way to word this is, where on this graph are we going to be plotting a point that's above the x-axis? Well, it looks like anywhere that's between -2 and 2, I'm going to be above the x-axis there. All right, so that's going to be my answer. The domain of f is the set of all x such that x is between -2 and 2. Okay, let's take a look at this next. Here's a definition. It says if the base of a logarithmic function is e, the number e, then we call it the natural logarithmic function. For notation, you're going to write the ln of x to mean log base e of x. Okay, the ln notation is used in every math book. Okay, so if I have y equals log base e of x, that means the same thing as y equals the ln of x. Okay, and y equals the ln of x means that x equals e to the y, if I'm using the definition of a logarithm. Now here's the phrase if and only if, again, so I can read this beginning to end, how I just read it, or I can read this end to beginning, and it means the same thing. Okay, so if x equals e to the y, then y equals the ln of x. Okay, let's go ahead and graph y equals the ln of x. To have us first graph y equals the ln of x, I'm going to have us regraph y equals e to the x. Okay, we did this in sections 4.1 and 4.2. Okay, and I'm just going to use the same 5 numbers that we had used there to get the graph of y equals e to the x. So if x is -2, e to the negative second power, that is 0.14. So there's -2.14. If x is -1, e to the negative first power is 0.37. So there's -1.37. If x is 0, anything to the 0 power is 1. So this curve is going to cross to the y-axis at 0, 1. If x is 1, we get e. E is roughly about 2.72. Okay, so there's 1 e on the graph. And then if x is 2, e squared is about 7.39. And that point is off the scale that I've got there. Okay, but here's where the output values are going to be getting very large. So the curve is coming along in quadrant 2 and it's rising slightly. It's going to cross to the y-axis at 0, 1. And then after we cross through at that spot, we're going to shoot upward and outward into quadrant 1. Okay. Also, there's a horizontal asymptote on the x-axis, right? Y equals 0. So, you know, x can be positive or negative or 0. It does not matter. We're not going to get 0 or a negative coming out of this. Okay. So we're going to get closer and closer to the x-axis, but we're never going to get there. Okay, so that's the graph of y equals e to the x. We have been there and done that before, right? We did that in section 4.1 and 4.2. Okay, now I want us to graph y equals the ln of x. Y equals e to the x is the inverse of y equals the ln of x. Okay, so there's the word inverse again. All I mean by inverse is that I'm switching x and y. Okay, so if I want to graph y equals the ln of x, which I do here, I'm going to have to graph the inverse function of y equals e to the x. So let's go ahead and switch all these coordinates and we'll plot the new points. -2.14 is going to be at 0.14, -2. -1.37 is going to be at 0.37, -1. 0, 1 is going to be at 1, 0. 1e is going to be at e1. And then 2, 7.39 is going to be at 7.392. That's off the scale here. Okay, but so then using those points, I can then draw the curve. Okay, so all I'm doing is I'm just flipping the x and y axis, flipping the x and y values to get the graph of the logarithm. Okay. Also, the horizontal asymptote that was on the graph of the exponential is going to turn into a vertical asymptote on the graph of this logarithm. And again, that's one of the features of a logarithmic curve, is that there will always be a vertical asymptote on the graph, just like there's always going to be a horizontal asymptote on the graph of an exponential. Okay, and here's the line y equals x. So, one way to say how I got the graph of y equals the ln of x was I took the graph of y equals e to the x and I rotated about the diagonal line. Okay, in other words, these two curves are symmetric about the diagonal line. That will always happen. So whenever you graph an exponential and a logarithm, its inverse, those two curves will always be symmetric about the diagonal line y equals x. Okay, now two quick things here. So I suppose that I could have already known the graph of y equals the ln of x. Why would I say that? Well, because earlier we graphed y equals 2 to the x. Okay, and 2 is really close to e, right? E is roughly about 2.72. So, having done this problem already, y equals the ln of x is going to look very similar to what we did over here. Okay, and that's exactly what happened. Now, another thing too, so I mentioned that the most common exponential is y equals e to the x. Okay, in other words, significantly more math problems are going to involve base e than any other base. Well, with that said, also, y equals the ln of x would be the most common logarithm. Okay, in other words, there's significantly many more math problems out there that involve base e, or we're using the logarithmic, the ln function, as opposed to any other base. So more than base 2, more than base 5, you're going to see base e more than those. Okay. In the next video, I'm going to talk about the properties of logarithms. Okay, and so we'll go ahead and stop this one right here, and we'll pick up with that in the next video.